Okay, great.
Okay.
Yeah.
So as the second speaker in this session, I would like to introduce Joe Hendrix, who is going to talk about verified decompilation using Lean 4.
Yeah, thank you. Yeah, so this is going to be a pretty high-level talk that's talking about the work we've been doing at Galois using Lean 4. And I'd be happy to kind of answer more detailed questions offline, and or if you have questions during the presentation. So let's kind of get started here. So first, I wanted to kind of give acknowledgements. This work is sponsored by the Office of Naval Research, and we're grateful for their support. Most of what I'm going to be talking about with regards to Lean 4 was implemented by Andrew and Simon, and we've had a number of contributors as well on this project. Leda, Jason, and Andre have helped in different Lean 4 aspects. We're also, of course, grateful for the support from Leo and Sebastian on Lean 4 itself, as well as the CVC4 team. And most recently, as of I think last night, we've started finally switching over to this other x86 formalization, and we've gotten some help with that from Sandeep Dasgupta from UIUC, I think now at Google. Just to say a little bit more about Galois in general before I dive into decompilation, we're essentially a consulting company, and we're organized around a particular mission, which is that we want that trusted systems, which are systems we trust, are actually trustworthy. As a consulting company, we're not ourselves building that many trusted systems, but we're mostly focused on consulting tools, techniques, and system demonstrations to show how one might build things. And so the interest in Lean is that it's my main personal interest is that it's a language that we think we can use for systems development, tool development, and it has this strong verification capability built into it. So the programming language plus prover is core to us. We try to contribute heavily to open source. I think that's part of trying to evangelize formal methods and other cryptography and other techniques to try to build higher assurance systems. And instead of sort of having our own proprietary products, we use spin-outs. And we kind of work in a bunch of areas all around trust and trustworthiness. At Galois, in terms of our Lean usage, we've been using it for quite a while. I think I first started using Lean with Lean 2, but we had our first projects with Lean 3. I'd also say that Lean's been, even not in its use, it's heavily inspired dependent calculus we have in our program verification tools called SAW, and the core calculus in that is SAW core, which is a dependently typed language. So I've learned a lot from looking at how Lean makes different choices, and we've worked to make it more compatible with Lean as we've had time to continue to refactor that. There's also interest in other theorem provers here, so we're not just a Lean shop. But the work I'm going to talk about today is mostly this Decompiler verifier. And so I think before diving right into that, I was going to talk generally about what decompilation is, why we care about assurance, and what I see as kind of the challenges there. So what I have here is a diagram showing kind of the steps that a source program goes through, just a C or a C++ program will typically go through in order to get an executable. And so you have a bunch of header files that come from the operating system and other libraries. You have source code that goes through a front-end lowering process in LLVM, which is part of CLang. You end up with this LLVM bitcode. This is very non-trivial, particularly for C++. That once you have the LLVM bitcode, that goes through optimization, repeated optimization, machine code generation, and then finally going into actually assembling the different machine code, which is often in a text format, into object files. And object files have bits of code, bits of data in them, and a lot of information of how you can move that code around and how you can include it, which that together with libraries in the system flows to the linker, which sort of does linking and does some use analysis, so it might be able to throw away some of the unused parts. But it's pretty coarse grained, and ultimately you get an executable out of it. So I think for the computer scientists, this is very basic, and for the sort of pure mathematicians, this is something you might not be super familiar with, but that's roughly what the tool chain is. And so for decompilation, what we want to do is reverse this process. And now each of these steps is lossy in different ways, so it really can't be done in general. But for many programs, we think we can get something useful out of that. And so to talk about that, I need to talk about kind of our use cases. So traditionally, and like actually what currently people are using decompilers for is largely program understanding, for reverse engineering or understanding malware, just understanding how is the system working, what are its bugs, so on. And so in this, it's very important that you decompile to a language that's understandable by people. It doesn't have to be the original source, and indeed you're almost never going to be able to decompile exactly to the original source, but it has to be something that a person can understand. This process of generating something that's understandable uses a bunch of uses static analysis, a lot of points to it, like different static analysis techniques, some heuristics, and some hints from the user. So it typically is an interactive process. So you have a full sort of integrated decompiler environment like IdaPro or Binary Ninja or Ghidra that helps you sort of do this. Soundness is very important, but it's not quite as essential as the other application that we're kind of looking into, which is we want to take a decompile program so that we can recompile an application. And there's a bunch of reasons why this would be very nice to be able to do. So one is you have like a legacy application, and you now have new compiler technology or new maybe new instructions that will add additional security protection. So you want to recompile the application and insert those into the original binary. And if you have the source, you don't need to do this, but frequently people have these large systems. They might have some of the source, but they don't necessarily have the entire source, or they might have all the build system and the build environments. And so they don't want to just recompile the thing from scratch and put it on their critical system. They want to do small patches or have like an automated way that sort of tailors what they're recompiling to try to preserve as much as they can. You might want to just patch an existing binary. So you have some device that isn't supported by the manufacturer anymore, but it talks to the internet. You want to patch that. This is another use case. And you could potentially use this type of technology that is under development to port binaries from one platform to another as you upgrade. Now these applications are, this is very different from the reverse engineering use case, because in this case, we don't necessarily need to go up to something that's human understandable. We're not trying to optimize that. What we need is a format to go up to a level that a compiler can understand, or perhaps only the linker can understand if you just need to relink things. But assurance is extremely important, because this is an application that was working. We're going to run it through this complicated tool. We hope it continues to work and we don't introduce bugs in the process of doing that. So assurance is essential, particularly if you're talking about like a really critical system. And I should say this is still as far as I can know, this is still sort of a research topic and a research agenda trying to build this. It's not I don't think people are currently doing this for their industrial control software. But if you're an industrial control engineer and are using this, I'd love to hear about it. So as a step towards this vision, we've at Galois we've built a tool. It's publicly available that basically does this. It's called Reopt for reoptimization. It takes an application, it does a process that I'm going to describe in a bit, reruns the LLVM optimization, and then produces a new optimized binary. And we're also, I should also mention, we've been working with SRI on this work. So they have a super compilation tool called Occam that is Reopt doesn't yet fully integrate with, but we're working on getting that. But that's the idea will be you can sort of retailor your binaries to work for a specific mission. Now to sort of talk through at a very high level of what Reopt does for decompilation, I wanted to show this diagram that sort of shows kind of all some of the major structures involved. So if you have like an ELF executable, so that's ELF is the name of the format that binaries are stored in when you run them on Linux. There's a separate one for OS X, which is the Mako format, and there's Windows has the PE format that's dominant, and there are other formats like the traditional A.ALF that technically are supported, but everybody on Linux is using ELF these days. And so, anyways, that is that binary. The first thing we have to do is we have to sort of parse that and start to extract interpret the different contents of that. And there's a bunch of things in there. There's sort of what are called the program headers, which is what the tool that's called the loader, which sort of generates the memory image of the binary, looks at. There's the text section, which has your source code, the machine code for your program, along with some padding spaces interleaved, and potentially jump tables are in there as well. The EH frame, which tells the runtime system how to unwind stack frames when an exception occurs, and this is in its own complicated format based on this dwarf debugging standard. You have what are the init, constructors, and detours sections, which are special routines that get called before main. You have your data, your BSS, which is just some zero initialized data, debug information, relocations, which are used to give it a dynamic linked executable, symbol table, version information, so that you know, like when you're linking, which versions you actually depend on. And then your section headers, which are typically used by development tools to understand the structure of your binary. So that there's sort of like two tables of contents within a single file, and the use cases are the loader versus the development tools. So we parse all this stuff, and I've probably had a lot of the gray hair I now have is from trying to read the documentation figure out what these actually formats are. Okay, so once you have that, you then decompile. We then have to decompile the application. And so for this, we sort of have an initial list of function entry points that we get from the symbol tables or start. We run a decompiler, and we have our own semantics that we've kind of tuned. There's plenty of quite good documentation from Intel about the instruction set architecture and the formats and the semantics. It's just very, very verbose. I think it's around 6,000 pages or so. But I don't really want to say anything bad about that, because they've clearly invested a lot of resources in documenting their instruction set and decoding it. And so what Reopt ultimately produces out of this is sort of a micro-op language, where each machine code instruction gets turned into kind of some register assignments plus some basic mathematical operations. We also will recognize control flow transfers like calls and returns, jump tables, and so on. And so we kind of have to analyze the semantics of the machine code to figure that out. Now, once we have this is kind of our low-level representation, and we can feed that into our verification tools. But for Reopt's purposes, it then does a second sort of analysis pass on the whole program, where it starts to identify for each function what are the arguments, how is the stack being used. So we can track. We basically can treat registers and static stack offsets as just variables. And then when we can do that to sort of reconstruct a function where we now have call statements and jumps, and it's sort of our pre-LLVM state, and then we sort of pretty print that and get LLVM bytecode. And now this pipeline here is pretty complex. It's been a lot of guess and check in terms of figuring out how to make things work, but it's working on Small binaries, there's a bunch of things I have on my roadmap of supporting, like var functions, functions that do more sophisticated stack allocations and such as set jump, long jump, things like that. But that's our pipeline that we've built out. And because of this complexity and because of this need to have a verification, I wanted to figure out a way to actually know that when we produce these LLVM, we were getting correct code, because I had certainly had cases where I ran the tool, got some LLVM, linked it again into the object, into an object file, and linked it in, and it would crash, and I would debug it. So we don't want end users to experience the same thing that developers of the tool are trying to face. So the first thing I want to talk about is what do we mean by soundness for a tool like this. So there's sort of these two use cases we have in mind. I'm targeting the first one primarily right now, which is that sort of recompilation soundness. And the idea is that every observable execution in that original binary that we had, or sorry, I did the opposite way. Every observable execution in the LLVM code that we have, so that new program we generated, there should be some corresponding trace in the original machine code that has the same observable effects. So we'll be working on formalizing this in Lean 4, and as I'll discuss in a bit. But this is the fundamental property we need. So it's possible that the machine code that we the LLVM we get out has fewer behaviors. And that can actually come up if, like, technically register in the x86 semantics is undefined after some operation, and we set it to 0. I don't know of any examples where we're currently depending on that, but that's sort of what that loss of precision would be. Now, from a verification standpoint, like if you're trying to verify the machine code program and you have an LLVM verification tool, what you actually care about is a different property, which is that if a property is true of the raise program, that should be true of the machine code program. And I think for properties where we're talking about trace-based properties, like about all the executions as opposed to tree logic properties, this is basically kind of the inverse of that formula I have above, where every execution in the machine code level, there should be one at the LLVM level. And I realized I have a typo. I should have wrote the machine code program here, and that's probably confusing people. Apologies. Now so in terms of what we mean by equivalence, our current notion of equivalence is based on event traces, and the events we're using are writes to non-stack addresses. So we allow stack writes to go away, stack operations that may remain signals like divide by 0, system calls. I should also add any call really is observable with the way we're doing things now, but strictly speaking, we don't necessarily need those. By having a more refined notion of observational equivalence, we just require the programs agree more. So it's always possible to add extra events to this. What we don't want to have is system calls that appear in one but don't in the other, and so on. Now, I thought about two different approaches for doing this. So the first that kind of immediately comes to mind is, well, let's just port this whole Haskell code base to a theorem prover and verify that. The challenge with that is my experience so far has been decompilation is a very open-ended problem. I mean, I think if you take various sub-problems, there's clearly undecidable problems here. It's quite complex to implement, and I find that we're continuing to improve it. Like currently, I'm working on some things involving exception table support. The second approach, which is the one we ended up choosing, is to build an automatic checker to check that the programs are equivalent. And now it is another typo. Program equivalence is ordinarily undecidable. But the decompiler output, in this case, since we're producing the binary or the LVM, it's very structurally similar to that input binary. So because of this, we can take advantage of this, and we've developed a computational approach that checks equivalence of the overall program by checking equivalence of the corresponding machine code and LLVM blocks using SMT solve. And so what this tool we've built takes in the original binary. It takes the annotations that come out of Reopt, and it takes the generated LLVM. It funnels those through. It uses the annotations to match up machine code segment region of the code segment into the LLVM, and basically emits a bunch of SMT problems. And the correctness claim we make is that if all the SMT set problems, all the SAT checks in them are unsat, then the generated LLVM is a refinement of the original binary. So it's sound for recompilation. And now, in order to make this compositional proof work, we had to develop, we had to enrich kind of the set of proof obligations. So we have a bunch of things about what's called the application binary interface, which describes how arguments are passed, what registers are saved by the caller versus the callee. We also have some assumptions about the stack having unallocated guard pages and some checks that we don't jump way out of the stack frame. So this is a fairly technical thing. And then we have to generate these block annotations that describe for each of these. Because of this, we have to generate our block annotations have to describe how the callee saved registers are stored across each block. And so we have kind of we have kind of this inductive invariant essentially. And so to sort of give you our current status is Reopt is generating these annotation files. We've tested this on small test programs. We're currently working through debugging this on a larger web server example. And I think when we have that, I'll sort of declare my first milestone 1 release. And sort of to give you some rough code statistics, right now Reopt is about 134,000 lines of Haskell, plus it's supporting machine code libraries. Reopt BCG, without the x86 semantics is 23,000 lines, and then with the K semantics is 62,000 lines. And so Lean is currently compiling this, Lean 4 is compiling this just fine, and we're able to use Reopt BCG. So it's available here. I should say it's still under active development. I'm happy to answer questions if you run into them. As part of this, as we sort of make these things mature, we're going to try to make our libraries available and externalizable. So we have libraries for LLVM parsing, ELF object file parsing, x86 64 machine code generation. That's using the UIC K semantics, and then SMT lib generation. So we would like to contribute these back to the community as the Lean 4 community starts to build up. And in terms of the planned work, there's just always constantly work we can do to expand the scope of the programs we can decompile and verify. I think one of the things the bigger things I'm most excited about is I just started to think about type analysis of the heap. And this turns out to be really important for verification of programs with indirect function calls, among other things, as well as sharing better LLVM. We're also working on formalizing the correctness of Reopt, and that's essential for us to verify things. The last thing I thought I'd say about is as another project we have ongoing at Galois. I just have a single slide, so I'll finish up pretty quickly. But we're working on getting Lean 4 program controlling a robot. Andrew Kent, who I think Leo mentioned a couple times in his presentation on Monday, is driving this. And so we currently have it working on a Raspberry Pi that can then talk over Bluetooth to an Arduino on this commercial robot. And I think we just have to get the full controller sort of ported from C to Lean so we can have it standing upright. But we'll make that publicly available too once that's available. I think the point of this exercise is to show, like, yes, Lean is a real world programming language, and that you can have a physical robot being controlled by a Lean program. So that's it. Yeah, thanks for your attention, and I think I'm way over. So if you have any short questions.
No, you're actually not over because we started so
okay.
late. So let's thank the speaker. Are there Any questions for Joe Hendrix?
I got one. Have you ever worked with functional languages and tried to convert something that was tail call optimized and then it didn't come out tail call optimized on the other end? Did you like run into a problem like that anywhere along the line?
Oh, yeah, it's I don't know if I can exactly answer. I think one thing I have noticed a few times is I split my time between like developing in a bunch of languages. We've definitely found with like Lean, I'm a big fan of Lean 4's kind of default strict evaluation. But I've definitely noticed sometimes with the writing a program in a certain like very lazy Haskell style will end up in Lean not using a lot more stack space than I intended. And so I think it'll be interesting to see if like the Haskell community moves over to Lean, like how much that affects the types of programs people write and issues they run into. But yeah, definitely there's lots of unexpected performance things as we change from functional to imperative and different evaluation strategies.
Thanks.
I had a question. So your original statement of the property of this program that you wanted, at first it seemed like that would be sort of trivially impossible to satisfy because the x86 has lots of sort of extraneous observable behaviors. So, you could have a function that just randomly decides to read one of its, like read RIP -1000, and who knows what's there. And then even if you just remove one instruction in the middle of your code, like that could totally change anything in the program. Like how do you make sure that you, especially like, malware style programs, like how could you possibly ensure that you won't break anything when you make any changes?
Yeah, so in that case, I would opt out of decompiling that particular program. So I think this wouldn't be an acceptable solution if you're writing IDA Pro and you're doing malware analysis, but we're not really targeting that use case for the decompiler. So essentially, we handle a subset of potential x86 functions, and we want to be sound on that subset. And it's in my view, it's always okay for us to say this is not a function we can accept. And so I think what that manifests, let's say we like had a bug and we did decompile that read of RIP into some read. Technically, I think, well, in that case, it's actually a constant, so it's going to read some read-only memory, so we could replace it with a constant. But let's say we had some other thing, like we're reading some random offset of the stack pointer. The Reopt BCG should catch that, because we don't have a good way of expressing that in LLVM that would be equivalent to the machine code program. So we would get a verification failure at that point.
Okay, thank you.
Does that answer your question?
Yeah.
Okay.
I have a question. Thank you for that informative answer. As somebody who's been looking at a lot of malware through IDA Pro, I can appreciate some of the complexities you must have come across. But even debugging normal programs, you have things like undefined accesses to memory. That how do these manifest in your verification procedure?
Yeah, so this is a little bit of a topic of conversation, because I'm not completely satisfied with our answers. So if the memory, part of what Reopt does is it attempts to distinguish between stack accesses and heap or non-stack accesses, which would just typically are the heap. And when with stack accesses, we have one sort of set of equivalences. With the heap access, my underlying assumption is that the decompiler the machine code and the LLVM are going to have the same heap shape, or potentially have the same heap shapes. So all we need to know is that the LLVM and the machine code are accessing the same heap offsets. So we can check from an exact pointer equivalence. As part of this, we in order to show soundness of this, we have a restriction that we're not able to handle programs that store references to the stack pointer in the heap. And we have an escape analysis to try to detect that. This is where, if we had this fancy type analysis, I think we might be able to, where we could analyze shapes of the heap, we might be able to do better than that, but we currently are gonna have to flag whenever the stack pointer escapes because you write that to the heap. It's certainly a risky thing to do, to store some like statically allocated variable in the heap, but I'm sure programs do it sometimes. So that's a limitation we have. Did that answer your question?
Well, yeah, yes, thank you. I was thinking more of things like just normal bugs, like things like undefined variables which are accessed before they're defined. I mean, these happen all the time.
Yeah. So programs. Yeah, since we're decompiling, we don't. We'll know what that value was. I guess if you access, if you have a machine code that access uninitialized value, I'm trying to think of what we would do there. I'll have to run that and check. I think in that case we would pick a default value for it, but I'm not 100% certain.
Okay, cool. And I find this fascinating. Thank you for your answer, and thank you for your presentation.
Sure.
Okay, if there are any other questions, let's ask them in the break. So let's thank Joe Hendrix one more time.